Okay, let's do a few more of these problems we've been working on. Except now let's look at maybe a couple of cosine examples. And then we'll move on to some other stuff. I'm looking at problem maybe 29. The cosine of the inverse cosine so once again, I want to first check if I meet the conditions, then this ends up being a cancellation rule and becomes very simple. And the cancellation rule for cosine is just like sine. For this condition, if this thing is between -1 and 1, then it's the pass-through. And this actually is less than 1. So I can simply say this equals square root of 3 over 2. I'm not going to do an example now, but if I did an example where the number inside the inverse cosine function is larger than 1 or smaller than -1, then there would be no solution. Now the flip side, let's do one of those. How about the inverse cosine of the cosine of 2 pi over 3. Now for this, the limitation is for the cancellation rule, this angle has to be between 0 and pi. It's really following the same sort of limitations as when we did the inverse cosine function. Now because 2 pi over 3 is between 0 and pi, I can right away give this answer. However, I want to find this problem. The inverse cosine of the cosine of 2 pi. Well, my initial angle here is not between 0 and pi, so I cannot use what I call the cancellation rule. But in this case, I can go ahead and still come up with an answer. So I simply ask myself, well, what's the cosine of 2 pi? Cosine of 2 pi is actually 1. So this now becomes a problem of what's the inverse cosine of 1? So that says, okay, I'm going to look for the angle. I'm going to take the cosine is equal to 1. That's pretty simple, right? The cosine is 1 right here. And that's an angle of 0. So I say this whole thing actually equals 0. Now the next kind of problem we have, these get a little trickier. For instance, I'm looking at problem number 35. Starts out with an inverse sine, but now I'm sort of mixing up different trig functions. Up until now, we've had inverse trig functions and then the same trig function together. Now, the inverse sine of the cosine of pi over 6. Well, in this case, let's just do sort of what it says. what is the cosine of pi over 6? We know that from our unit circle. Cosine of pi over 6 is square root of 3 over 2. So now this, in a sense, becomes a problem of what's the inverse sine of square root of 3 over 2. So now, we go back to our unit circle and we say, let's go find an angle where the inverse sine is square root of 3 over 2. Although now, since we're taking an inverse sine function, we have the limitation that that angle has to be between negative pi over 2 and pi over 2. So for what angle is the sine square root of 3 over 2? Well, it's up here at pi over 3 and also 2 pi over 3. But 2 pi over 3 is not acceptable because it's outside the interval. So therefore, the answer is just pi over 3. All right. That's not too bad. Let's take a see what else we have. How about the all right, here's where it gets a little tricky. Let's just go and dive into one of these. Number 37 says the sine of the inverse cosine of 4/5. Now the problem is, the inverse cosine of 4/5, that is not one of my values that I've memorized from the unit circle. In other words, if I ask myself, I know this whole thing here is going to be an angle. Whenever you take an inverse trig function, the answer is an angle. So what I ask myself is, let's go find an angle so that when you take the cosine of the angle, it equals 4/5. Well, I don't know the answer to that off the top of my head. That's not one of my points on the unit circle. I'm sort of stuck. So what you do is, you take this little fact and you go create a right triangle, just like we did when we first started working with trig functions. And since we're talking about cosine, I'll say here's my angle. Another way to write this is basically the cosine of theta equals 4/5. So if I think about this right triangle, cosine of theta is 4/5, cosine is ka, adjacent over hypotenuse. Now if I complete this right triangle, this is a 3, 4, 5. I know right away that this other side here is a 3. So here's the triangle that results from the inverse cosine of 4/5. And what's interesting is now, if I replace this with theta, my problem now becomes what's the sine of theta? And this theta is the theta for this triangle. It's almost like this inverse trig function allowed me to create my triangle with theta in it. So now I can say the sine of theta is what? Well, sine is opposite of hypotenuse. It's 3/5. And that's the answer. Let's do one more. How about number 38? The sine of the inverse tangent of 7/4. So this right here, since this is an inverse trig function, that whole thing is really going to be an angle. And I can see, if I can figure it out, I can ask myself, well, let's go find an angle that when you take the tangent at 7/4, but I have no idea what that is. Another way to think about it is what angle, when I take the tangent, it'd be 7/4. I don't know that. However, with this information, I can go ahead and create a triangle that has theta in it. Tangent of theta is 7/4. Tangent is TOA, opposite over adjacent. And then if I want to figure out the hypotenuse, the Pythagorean formula says 7 squared, which is 49, plus 4 squared, which is 16. Looks like it's a square root of 65 is my hypotenuse. So now, this inverse tan function allowed me to create this triangle, and now I can think of this problem as simply the sine of theta, where this is my theta here, and the sine is opposite over hypotenuse. So it's 7 over square root of 65. All right, so that's how you do those kinds of problems. A little tricky at first, but once you realize that you use the inside part to create your triangle, and once you create your triangle, then you can usually figure out the trig function pretty easily.